In today's session, we'll be delving into the architecture and characteristics of IoT for our valued audience. Let us talk about the things. A thing refers to an object embedded with sensors responsible for collecting data, which is then transmitted through a network, along with actuators enabling these things to take action. For instance, controlling the illumination, accessing doors, adjusting engine speed, and various other functions. This idea encompasses a wide array of items such as refrigerators, streetlights, buildings, vehicles, manufacturing machinery, rehabilitation devices, and virtually anything else conceivable. It's important to note that sensors aren't always directly connected or physically integrated with these objects. Entities, tangible items, and elements constituting the tangible realm, encompassing aspects such as temperature, gas emissions, humidity, pressure, pneumatic measures, mechanical sound, imagery, location data, and various other parameters. These components collectively form a crucial segment within a network of things. Let's explore the ubiquitous sensors extensively utilized in IoT-related devices referred to as sensors for things. These sensors detect physical attributes and transform them into electrical signals, commonly known as sensors or transducers. Examples include temperature sensors, pressure and altitude sensors, gas sensors, GPS sensors, and ultrasonic sensors. Let's delve into the structure and some key attributes of IoT. Now, we'll explore the utilization of gateways within IoT. Information flows between devices and the cloud bidirectionally via gateways. These gateways establish connectivity between devices and the cloud component of the IoT system. They facilitate preliminary processing and filtration of data before transmitting it to the cloud. Additionally, gateways are responsible for relaying control commands originating from the cloud to devices. Subsequently, the devices execute these commands utilizing their actuators. We'll now briefly examine the cloud gateways. These gateways play a pivotal role in compressing data and ensuring secure transmission between field gateways and cloud-based IoT servers. Additionally, they guarantee compatibility with diverse protocols, allowing communication with field gateways by adapting to supported protocols based on individual gateway capabilities. The streaming data processor ensures effective transition of input data to a data lake and control applications. No data can be occasionally lost or corrupted. A data lake serves as a repository for storing data produced by connected devices in its raw form. It aggregates various types of data generated by sensors, whether it arrives in batches or streams. To derive meaningful insights, data is extracted from the data lake and transferred to a big data warehouse when required. A big data warehouse is where refined and preprocessed data, essential for deriving valuable insights, is sourced from a data lake. Unlike a data lake that accumulates all types of sensor-generated data, a big data warehouse stores solely cleaned, structured, and correlated data. Within this warehouse, there's stored contextual information pertaining to devices and sensors, such as sensor deployment locations, as well as the instructions sent from control applications to these devices. Data analytics utilizes information sourced from the big data warehouse to identify trends and extract actionable insights. For instance, it enables the assessment of device performance, identifies inefficiencies, and devises strategies to enhance an IoT system, making it more reliable and customer-centric. Moreover, manually discovered correlations and patterns can aid in developing algorithms for control applications, further enriching the system. Machine learning, along with the models it generates, aims to produce more accurate and efficient models specifically for control applications. These models undergo regular updates, typically occurring at intervals such as weekly or monthly, drawing insights from historical data stored in a big data warehouse. Once data analysts verify and confirm the effectiveness and applicability of new models, control applications implement these approved models for use. Control applications are responsible for sending automated commands and alerts to actuators. For instance, in a smart home scenario, the windows could receive automated commands based on weather forecasts, opening or closing as necessary. When soil sensors detect dryness, automated commands could trigger watering systems to hydrate plants. Similarly, in industrial settings, sensors monitor equipment status, and if a potential malfunction is detected, the IoT system generates and sends automatic notifications to field engineers. To guarantee the effective operation of IoT devices, specific procedures are essential to manage the performance of interconnected devices. These procedures encompass various tasks. Device identification. This involves authenticating the identity of each device to confirm its legitimacy and ensure it operates with trusted software, transmitting dependable data. Configuration and control. Devices must be fine-tuned to align with the objectives of the IoT system. Some parameters, like a unique device ID, are set during installation, while other settings may require periodic updates, such as adjusting the frequency of transmitting data messages. Monitoring and diagnostics. Continuous monitoring is crucial to ensure the seamless and secure performance of each device within the network. This proactive approach helps mitigate the risk of malfunctions and breakdowns. Software updates and maintenance. Regular updates and maintenance routines are necessary to introduce new functionalities, rectify bugs, and address potential security vulnerabilities within the devices. Effectively managing users is crucial to maintain control over access within an IoT system. User management encompasses several key elements, including user identification, identifying individual users within the system, roles and access levels, assigning specific roles and determining access levels for each user, ownership attribution, establishing ownership rights and responsibilities within the system. Moreover, it involves tasks such as adding and removing users as required, administering user settings to tailor preferences and functionalities, regulating and restricting user access to specific information as needed, granting permissions for particular operations within the system, supervising and documenting user activities for security and auditing purposes, among other responsibilities. Security stands as a foremost concern within the realm of the Internet of Things, IoT. The interconnected nature of devices results in the generation of vast data volumes, necessitating secure transmission and protection from cyber threats. The vulnerability arises from the potential access that cybercriminals could gain to the core system of the entire IoT network, thereby seizing control. To counteract such threats, proactive measures can be taken. This includes logging and analyzing commands relayed from control applications to the connected devices. By scrutinizing user actions and storing this information securely in the cloud, potential security breaches can be identified at their nascent stages. This enables the implementation of measures to mitigate their impact, such as the restriction of specific commands emanating from control applications. Moreover, the identification of suspicious behavioral patterns is achievable through the collection and comparison of samples stored in the logs generated by IoT systems. This approach aids in the early prevention of potential breaches and serves to minimize their repercussions on the IoT infrastructure. Consider the scenario of intelligent lighting as an example. Its fundamental elements encompass sensors that gather environmental data, such as daylight levels, sounds, and human movements. Lamps are furnished with actuators responsible for toggling the light on and off. Raw data from these sensors is stored in a data lake, while a comprehensive repository, the Big Data Warehouse, houses refined information pertaining to residents' smart home activities across different days of the week, energy consumption, and additional relevant data. This scenario involves a system operated manually and monitored through manual means. Users manage a smart lighting system using a mobile application that includes a yard map. Through this app, users can visually track the status of lights, discerning which are currently on or off. Additionally, they can issue commands via the app to control applications, which then relay these instructions to lamp actuators. Furthermore, this application has the capability to indicate lamps that are nearing malfunction or potential failure. By examining users' utilization of smart lighting, their schedules, either input by users or inferred by the smart system, and data collected through sensors, data analysts can develop and regularly refine algorithms for control applications. The utilization of data analytics also aids in evaluating the efficiency of the IoT system and uncovering potential operational issues. For instance, if a user manually turns off a light immediately after the system automatically activates it, or vice versa, it may highlight deficiencies in the algorithms that require prompt attention and rectification. Let us try to understand the automation and associated pitfalls. Here we can see a scenario where a light sensor is available which can sense the natural light and send the data about the light to the IoT cloud. When the daylight is not enough, according to previously stated threshold, the control apps send automatic commands to the actuators to switch on the lamps. The rest of the time the lamps are switched off. However, consider a scenario involving streetlights where, during the nighttime, the light sensors erroneously detect light, leading the system to register this false signal and consequently switch off the compound lights despite the actual darkness prevailing at that time. Enhancing the smart system's comprehension of factors impacting lighting by accumulating relevant data in the cloud proves beneficial. When sensors are monitoring motions and sounds, a mere response of turning on lights upon detecting movements or sounds in the yard, or uniformly switching off all lamps in silence, falls short. Movements and sounds could stem from sources like pets. Therefore, cloud applications must discern between human movements or voices and those produced by pets. Similarly, noises originating from the street, neighboring houses, or other ambient sources necessitate differentiation. Addressing this concern involves storing samples of various sounds in the cloud and employing comparisons with sounds captured by the sensors to mitigate this issue effectively. Intelligent lighting leverages machine learning-generated models to, for instance, discern patterns in smart homeowners' behavior, such as leaving home at 8 a.m. and returning at 7 p.m., and adapt the timing of light activation and deactivation accordingly, example turning on lamps 5 minutes before they are typically required. By analyzing users' behavior over an extended period, a smart system can evolve its understanding of advanced behavior patterns. For instance, if sensors fail to detect typical movements and voices of residents, the smart system might infer that the occupants are on vacation and adjust its behavior accordingly. Moreover, it could intermittently activate lights to create an appearance of occupancy for security purposes, while also conserving energy by not leaving the lights on continuously. For efficient user management, the smart lighting system can incorporate multiple user roles to delineate control and access. Individuals designated as owners will possess comprehensive control privileges over the system. They can modify smart light behavior patterns, monitor the status of yard lamps, and set priorities for commands. In cases where conflicting commands arise from multiple users, an owner's command will take precedence for execution by the control applications. Those categorized as users will have access to a limited set of system functions. Inhabitants will be empowered to toggle lamps on and off but won't have the ability to alter settings. Guests will be granted access to switch lights on and off in specific areas of the house but won't have control over all lighting, such as those near the garage. Additionally, beyond role distribution, it's crucial to consider ownership. As these systems can potentially oversee a multitude of households, it's imperative that a resident of a smart home retains control over their lighting setup rather than that of a neighboring property. Thank you for joining us in this insightful session exploring the architecture and characteristics of IoT technology. We hope this discussion has provided valuable insights into the intricate world of interconnected devices. To stay updated with the latest trends, discussions, and informative content on IoT and related technologies, make sure to subscribe to iNet Tech Talk on YouTube. Don't miss out on upcoming sessions that delve deeper into the realms of innovation, security, and advancements within the IoT landscape. Remember, sharing knowledge empowers us all. Share this video session with your peers and colleagues who might benefit from understanding IoT architecture and its nuances. Subscribe now to iNet Tech Talk on YouTube, and together, let's continue exploring the limitless possibilities and advancements in the world of IoT. Thank you for being a part of our community.